All right. So I think we're live streaming. So I know Loren from grad school. He got his PhD somewhere around probably 03, 05, somewhere in there. I don't remember exactly. And then after that, I believe he went to France. He's been a community college teacher. Um, let's see. And now for a while, he was at Caltech. Now he's back at Caltech and Amazon in a joint employment. For a while, he was working for D-Wave. So he's seen a lot of different things. He's done a lot of different uh, real life jobs. And I think it's important that we talk to him a little bit just so that you can see, maybe to get some perspective on, school is a little bit silly sometimes and you forget about the big picture of someday getting a job. So, Loren, perhaps you could just start off by maybe telling us briefly about, I guess, your job or your career path or whatever you feel like. Whoops. And let me see if I can get you on the main screen. Just a second. There you are. Go for it.
Sure. So my background is in superconducting devices. So trying to use basically like aluminum or tantalum or some of these materials that start superconducting at low temperatures. And when they do that, you get some amazing effects. They have no loss. There's some electrical elements that you can make that you just can't make at room temperature. So you can make electrical circuits and detectors that are just otherwise impossible. And so, I've worked in a few different devices. I worked on making detectors for astronomy. So I went to telescopes and we fielded these systems to do, trying to image some of the earliest light from the universe. And then, so those are sort of detector applications. And then I switched over to working on quantum computing for the last, I don't know, eight years or something like that. So I've been working on quantum computing. And again, using superconducting materials to realize this. So, and the goal there is just, we have amazing computers now. You can do, we can sit at home during COVID and talk to each other over the internet. But there are some math problems there's actually most math problems we can't solve. Even like, delivery of packages, what's the best route? You can find pretty good solutions, but actually finding the best solution is a exponentially hard problem. So it just gets harder and harder as you add more destinations and more packages to deliver to find the best route. So, and that has real world implications in terms of, how much gas you use and how long it takes. So there's all these problems in the world that people want to solve, and they're very difficult even with our best classical computers. So quantum computers are another computing paradigm that, at least for some problem classes, should be able to solve what they say exponentially better than can be solved with classical computers.
Right
so
on.
That's what I work on.
That's a pretty good summary. And is it okay if I interrupt here, Loren?
Yeah, of course.
I was hoping I had a list of questions here. I thought I might just run them down here and then you could just answer off the cuff. And students, at some point, if you want to come up with your own questions, maybe you could just throw those in the chat there, or you could unmute. But I thought I asked some questions that might benefit everybody, so I thought we might start with those. And if these are bad questions, that's okay. So I'm curious if there's anything now this is a ways back, undergrad. Is there anything that you remember from undergrad that you're really glad you did or really wish you would have done that you didn't do, or anything like that? Because these students, obviously, they're freshman, sophomore level. Is there something that stands out?
I would have got a computer science degree and gone straight to Silicon Valley, and I'd already be retired. But even when I was in undergrad, it was pretty obvious that the internet was going to be huge. And I stuck with physics. Physics is intrinsically interesting, but to be honest, it's not going to be the highest paying field. Science in general does not pay that well. So if you want to get paid, I think, computer science is probably the best route, right?
Engineering as well.
Anything with physical hardware just isn't going to pay as well. That's all the profit margins in software, right? So, you do okay. Engineering does fine. You'll have a nice life. But if you want to make easy money, I guess nowadays it's in software, right? So I think the downside to being in software is it's always changing. So you got to be constantly sort of learning the latest libraries, the latest frameworks, and all that. But if you're happy to be learning, then I think it's a good area to be in. I think a lot of jobs, the other things are there's a lot of jobs that aren't going to go away. I think, anything that's like human based, like you're always going to go see a doctor. They might have new tools and there might be portions of their job that go away to computers, but there's always going to be a human aspect to that, or teaching, or any social type interactions. Those aren't going to be taken away by the internet, right? So, but yeah, so that's what I would have done differently in undergrad.
All
I
right.
think.
Is there anything you're glad that you did? Is there anything that stands out, or was there some skill, be it academic or personal, or anything that you learned as an undergrad or even into grad school that kind of you feel like helped you succeed in the workplace? Like what kinds of things are helping you succeed in the workplace that maybe you learned in school? Or
Yeah, I mean, I think having good social skills is something that you don't learn in physics, but definitely is important in the workplace, right? So being able to get along with your coworkers and see their perspective, and just having good emotional intelligence, I guess, is pretty important in the workplace, right? And then I think the other thing is getting hired. Well, just knowing what jobs are, like what people actually do and what their days like what does a job of a lawyer actually look like, or a psychiatrist, or a doctor, or a engineer, whatever, right? What does that actually look like on a day-to-day basis? I don't think I had a great understanding of that in undergraduate. I think it's worth trying to understand that better. And, like now you can probably go, I don't know, watch YouTube videos and people describe their jobs or their lives and think about whether that's really what you want to be doing, right? Yeah, and so then once I think the other thing is if you can figure out what you actually want to do, then really focusing in on that. I was always kind of wanted to do everything. So, I had 2 degrees and a minor in undergraduate, and kind of got really spread thin, and, did a lot of school, like, got a graduate degree and 2 postdocs, and that all kind of delayed sort of getting started in a career in a sense. Like if you really know what you want to do, just kind of go do that. I think it's going to, focus on the classes you need, go do that. And then I think you'll be probably pretty well off.
Would you say it's fair? A fair trade-off is if you know exactly what you want to do and you go into it, you're pretty much set. But I would argue that by you kind of having a diverse set of backgrounds and experiences, that perhaps makes it easier for you to change. Is that the trade-off, basically? Starting earlier, retiring earlier versus having more flexibility in career choice. Is that accurate or not really, in your opinion?
I don't know. I mean, I guess the other side of it is that I've had the opportunity personally to live a lot of places. So I lived in Santa Barbara, the Bay Area, France for a while, Los Angeles, Canada. So, my career path, I guess, has afforded me the opportunity to see a lot of the world and, meet a lot of people, which has been really nice. So that's nice. But, if you're moving a lot, changing countries, it makes it harder to sort of, well, yeah, I guess it makes it harder to sort of build your retirement package and all that, right? So, if you know what you want to do and you just go have one fixed career, stay in one place, buy a house, you're probably going to be able to retire earlier. And, so that's maybe the trade-off. I don't know.
Okay. All right. I was just curious. So, do you think grad school was worth it for you?
For me, maybe. I don't know. Like I've certainly enjoyed all the positions I've had. But so grad school is a lot of work, and in the sciences and engineering, generally you'll actually get paid, not much, but if you go into liberal arts graduate school, you're going to be paying for it, and that just seems like a bad value to me. Science, you're going to get paid a little bit. It's not very much, and it's So it's a lot of work and you're kind of struggling the whole time. So it's definitely like a, stressful situation. And then the amount of extra cash you make for having a PhD, right, isn't necessarily commensurate with those 5 years or whatever of lost earnings, right? So you really got to think hard. If you really love the field, then I think it's worth it. So for me, I really enjoyed learning and I enjoyed the experience, but it's definitely not the best financial decision, I would say.
What
For
about
everybody.
what about advancement? For example, you've worked a number of places. Do people with bachelor's
Mhm.
degrees get to advance to management and move up or not?
I think, well, so if you want to do management, I actually would highly suggest thinking about management school. Like it really
Like an
is,
MBA or something?
yeah, an MBA is definitely like there's a glass ceiling there or whatever, some kind of ceiling, right? So
Yeah.
if you have an MBA, and there, it is a real skill, right? Like, and I think, it's something that you need to learn how to do sort of project management and manage people, how do you get people to do stuff without pissing them off? And
Yeah.
that's not easy. And like being efficient and making sure things are, well scheduled on track. Like companies really highly value that. And so if you want to do that, if that's actually something you enjoy, then I think it's worth considering business school. I think it's 2 years, something like that. Uh, being a PhD, I am definitely afforded a lot more opportunities to choose what I work on. Generally, nobody ever tells me what to do. I just kind of pick what I want to work on. So,
Right.
but
So there's a little
yeah,
bit of
it doesn't
creative
necessarily,
freedom at a
exactly.
potentially lifetime's earning cost.
Yeah, exactly. I think
But
that's
so
it. I
for
mean,
you, it was a good trade.
yeah, it's nice to have that freedom. Yeah, it's definitely a trade-off though, right? So if you want to get high in the corporate ladder, you're not necessarily going to get that just by being a scientist or an engineer, right?
Yeah, I got you. Okay. Sorry if I'm hogging this class. I promise to get to your question soon. So I was hoping you might mention uh, what it's like trying to get a tech job these days. Obviously, COVID has changed things, and who knows what will be like in 5 years or 2 years even. But is there, and in particular, I was thinking about, is there anything that stands out about like the application process or their skills that basically disqualify people if you don't have them, or interviews, salary negotiation, anything that just comes to mind out of those?
Yeah, I could go through each of those. I think so. The
Okay.
application process, it's going to help to have a network, to have somebody that you know. Um,
Like
I
LinkedIn
think
or something
every,
like that?
yeah, just meeting people, having like, one of the biggest values of college is the people you meet. Um, every position I've gotten, I've known somebody there already.
Mm,
I have gotten interviews where I didn't know somebody, but it's much harder. You really have to stand out, right? So I think for the application, the application is most things are standard forms nowadays. There is if you're applying for any position, really, there's going to be an HR wall and a software wall. So the HR first is going to pass through some software filters just to see if you have the right keywords, the right things that match what's on the description of the job. So if you're writing a resume or a well, I don't know, a lot of places don't even use cover letters anymore, but if you're writing your resume, you want to tailor it to that job and that description to make sure it kind of at least gets considered. And then similarly, there's usually going to be somebody, once it gets through those software filters, somebody in HR that's actually going to uh, look at it closely to make sure it matches the description of the job well. And they might not even understand the position very well. They're just looking to see, does it match the job description? Because they're not necessarily an engineer or a scientist or whatever. They just want to see that whatever the hiring manager posted matches your background. So you want to make sure those kind of align pretty well. So assuming you make it through, what was your next thing on your list?
let's
Move your
see.
giant.
Sorry, yeah, move my giant head. Are there any like must-have skills? Obviously, that's very position dependent, but like, do they need
Yeah,
to know
yeah.
Python or not in general these days? Or obviously, yeah, any.
Well, so for software engineering, you don't necessarily have to know Python. There's a lot of different like if you're going to work on Apple products, you're probably going to want to know Swift. If you're going to want to go work for Google, you might want to know Go. You know, if you're going to do data science, Python's a great choice. Some scientists are moving to Julia. There's a lot of languages. JavaScript is the #1 language if you're going to do any internet programming, and even starting to be desktop programming. JavaScript's huge. So, you know, you want to know those languages. I don't think the specific language, you know, it's maybe good to pick a language that is popular if you're trying to get hired for a software job, but mostly knowing a few different languages and having experience with different paradigms of computing and programming is useful. So that's for software specific jobs. You know, if you're applying to be a fabrication engineer in a semiconductor foundry, you're going to want to know all your vacuum systems, all your deposition systems. If you're an electrical engineer, you're going to want to know your circuits really well. So you want to know all that, right? Whatever your job is.
So that's probably pretty hard to answer succinctly today.
Yeah.
All right. So how about interviews?
So again, for software specifically, there is very much a canned interview process. You can buy books. One of them's, I forget exactly, something the coding interview. Anyway, you just search Amazon. There's basically they're going to test you. They're going to give you a software test nowadays, and it's going to have like, can you write these algorithms, right? Can you write, they'll give you a list of names, and can you sort those names alphabetically efficiently? Or they're going to give you, so as part of the coding interview process, there is, probably a couple hundred questions that are very typical that you can learn and you should study. If you go to undergraduate for computer science, you're basically teaching that stuff. But you can learn that on your own too. And they will have live coding sessions. They're going to give you a problem. They're going to watch you code. And, I think the thing there is not to get nervous, talk through the problem. Just like in your physics exams, you're going to want to like write down the problem, write down your knowns, your unknowns, what you're trying to solve for, write through how you're going to try to solve this, even if you don't know how to solve it right away, like what's your approach. Then write out a basic example, the maybe not the best or most elegant way to solve it, but just the, like some brute force method, right? And then try to improve it from there. So I think that's kind of the general strategy. And then your last point, salary negotiation. I think, again, you're dealing with HR usually, not the hiring manager. So I think you should. I think a lot of times you get in a situation where you're worried about not getting the job or seeming to be too greedy or something like that. But I think it's important to remember you're at that point. You should go for sort of as much money as you think you confidently can. It's not going to reflect badly on you or anything like that. So you should try to always, you're just dealing with the HR. Like once they just want to get you hired. Like if you get to the point you're at the salary negotiation, they've already decided they want to hire you, and they're just trying to get you, at a, they don't even necessarily want the lowest cost. They want you to be happy at the lowest cost they can get, right? So they definitely want you to be happy. So, because they don't want you to just be like, find out that your salary is low and they go to another company. They lose a lot of intellectual capital, a lot of training, et cetera. So typically they want, they want you to be happy, and then the lowest value they can get for that. So
when you were trying to negotiate salary, how did you figure out a reasonable number? Did you just kind of search the internet for comparable positions? It's like not everything is out there, right? Or did you just ask friends or?
Yeah. Well, the couple times I've done it, I had some ballpark estimate in mind, and you do look at the internet. If you're in like a software job, there's gonna be a lot of information. Or if you're in a standard kind of position, if you're trying to be an account manager or in accounting or something, there's going to be a lot of information. If you're more specific, that like the more specific you are, the less type of people that are like you out there, the less information. And so you kind of have to just try to figure it out as best you can and what you'll be happy with. Yeah, I mean, like when I went to Canada, I got what I thought was a great salary, and then the Canadian dollar crashed. So you gotta always remember, outside considerations too, right? Like what is the cost of living in an area? What are, the industry, is the industry, going up? Should you expect your salary to go up? And then a lot of times, at least with tech jobs nowadays, there's the base salary, and then there'll be stock options and things like that. And so your base salary won't be necessarily that great, and a lot of it'll be in stock options and end of year rewards, things like that, bonuses. So and that's all negotiated as well. So you just have to kind of know all that package, what you're expecting.
Fortunately, they've got a couple of years to figure all that out. But so basically, would you say it's safe to say that, as like a micro summary, don't forget about salary negotiations and read about that and learn about that when you get your first job?
Yeah, and don't it's okay to be. You should feel
slightly aggressive, be a little greedy.
Yeah, you should be. Yeah.
Sort of like people are afraid to talk themselves up in their resume. They shouldn't be. You got to sell yourself on your resume and then sell yourself in the salary negotiation phase too.
Yeah, sell yourself within bounds, right? Like you don't want to go too crazy. You don't want to lie, and you don't want to, but you want to push the boundary a little bit there. Yeah.
Okay. How much of your job is the following? Well, you're probably coding a lot, but I'm curious about writing, reading, and presenting. Do you have to like just out of a day-to-day basis, do you spend more of your time presenting or not? Or I'm just curious.
Yeah, well, so this is going to be true of data science, engineering, any physical sciences. You're going to spend some percent of your time figuring out how to do experiments and taking data and that sort of thing. And then you're going to spend more than half your time justifying it, like writing to justify why to work on that, presenting the results, and discussing with other people. So, as a scientist, you're still going to spend most of your time trying to sort of interacting with other people. So I'm kind of lucky in that I can spend a lot of my time just reading articles or kind of choosing what I want to work on. If I want to work on programming, if I want to work on, so I have sort of a lot of latitude, but nonetheless, at the end of the day, like I do end up, sort of communicating with other people a lot. So that's going to be any company. It's a n factorial problem. As you add more and more people to the company, if you want everybody to know everything, you kind of have to communicate more. So you try to have teams and partition things off, but it's there's always going to be a lot of communication, right? Just so everybody's not confused what's going on.
So Gonzalo's got a question. You want to just unmute and say it, Gonzalo?
Yeah. So in layman's terms, can you describe what quantum computing is to us?
Yeah, sure. So, I mean, so this is always difficult, but the first thing to realize is sort of what a classical computer is doing, right? So your numbers in classical computers are represented as a 0 or a 1. It's just those two states. Whereas a qubit can have 0 or 1 or what's called a superposition. It's a linear system, so you can have, just like in waves, like in water waves, you can add waves together. You can also have this wave function describing your information. So you can have a superposition of the 0 and 1. So it can be both. It's usually said as can be both 0 and 1 at the same time. It's not quite true, but it's something like that. So you can already see that just that has a higher density of information encoded in the basic element of a quantum computer. So these are called qubits or quantum bits, and they have a higher density of information. They don't have just 0 and 1. They can have any of these kind of combinations of them. And then you interact them, and they also have sort of wave-like properties. They interfere, and that interference is you're basically trying to solve problems by setting up the interference where the right answer, just like light, you can get light interfering, get a bright spot, and you can have destructive interference and get a dark spot. You're trying to get your solutions to your problem to interfere and be sort of bright spots. So that's kind of the simplest description of what a quantum computer is actually doing. But basically, there's another side to it. Is like, why do we want to build these, or what are the applications? And I think there's two major applications that people are really excited about. The original was the Shor's algorithm, which was a new algorithm for factoring numbers into their prime constituents. So like taking the number 9 and factoring that into 3 and 3. That, it's easy to do if it's a small number, but now if it's like, 10,573,852, like factoring that into its prime numbers is gets to be it's exponentially hard on a classical computer. It gets harder and harder, and we in fact can't do it for very large numbers. And that's all the internet's security is based on that factoring problem. The RSA encryption algorithm uses factoring at its core. So quantum computers can actually do that in principle. Nobody's been able to do this for any large numbers. For small numbers, people have done it, but for large numbers, nobody can do it yet on a quantum computer. But in principle, it's exponentially easier. So it actually goes, so all of our internet encryption, if you had a really good quantum computer right now, would be broken. We'd be able to unencrypt everything that's being sent over the internet. So that was one algorithm that really motivated people to start working on quantum computing. The other thing that I think people are really motivated on in terms of applications is simulating quantum systems. So if you want to design a new drug, like a pharmaceutical company, you're gonna have a whole bunch of atoms, right? And you want them to interact with each other. And what you want to really find out in the end is these electronic states. So just like a neon light, you put a voltage across that and it excites the neon atoms. And the electrons go to a higher excited state, and then it falls back down and emits that neon light that you see, right, with neon lights. So that electronic structure, like what color of light's going to come out, that comes from atomic theory. But now if you build up molecules, they'll have similar things where you want to know what is the electronic structure and what sort of, like what type of light would a molecule emit. So that problem turns out you have to solve all of quantum mechanics completely and correctly, and it turns out you can only do that for small systems. Even 50, even 50 atoms is basically out of reach of classical computers today. And so solving the full Schrodinger equation for 80 atoms would take something like all the particles in the universe. So whereas with a quantum computer, it would take 80 qubits, right? So it's really it's a massive speed up for quantum simulation if you could build and design qubits that are robust. And that's the real engineering challenge that everybody's working on now. So we can make qubits and they work fine if you have 1 or 2 of them, but they don't, that superposition of being 0 and 1 at the same time is incredibly sensitive to noise in the surrounding world, and it tends to lose that information pretty easily. And so people are working on different physical implementations, just like it took a long time to find the transistor that revolutionized computing, where people were using vacuum tubes before that, and even mechanical switches. It took a long time to find something that really worked for classical computers. Quantum computers were still in that same era of finding the physical, information storage unit that is really quite robust to noise and can be used for computation. So that's kind of where things are at. And there's 3 companies that have kind of a similar approach, or 2. Well, Google, IBM, and this company Rigetti are all using a single approach. Amazon's we're doing something different that's trying to build in error corrections. So you can, built into this qubit, it's more robust to noise. And if you do have noise, you can correct for that noise. So those are all using superconducting qubits. And then there's other people working on using, so superconducting qubits, you're using superconducting wire to store that information, like in a loop or something like that. Whereas other people are using fundamental particles like photons of light or ions, so single ionized atoms, things like this, to try to be the information storage unit that forms your qubits. So there's, I think I last heard there's more than 150 quantum computing companies at this point.
Wow.
And then there's also quantum communication, which is a separate thing of, can you send photons that are storing this special information? Can you send that over long distances? And in fact, China's well ahead of everybody else in that field. They've been able to send what are called entangled states, these qubits that are interacting and storing this information to space and back already over
Wow.
satellites. So,
Really?
yeah, and so they can do quantum key distribution. So yeah, China's leading the world in that, which in terms of getting US dollar funding is actually good. It's scaring the US government, so they're throwing more money at it. But
so I see that Angel's asked a question in the chat, and then Christian has a question. Let me do Angel's first here. He says, what does your day-to-day routine look like? And I think you've kind of been describing some of the projects you work on there. But are you doing okay on time, Loren? Do you need to get out of here soon, or?
No, I'm fine.
Okay.
Let me know if you have classwork you have to actually do.
Yeah, we'll probably, let's shoot for about 10 more minutes. Does that sound good?
Sure.
All right.
Yeah.
So yeah, go ahead.
So my day-to-day routine starts with my children yelling at me, screaming and running around the house. And then so then I get out of the house and as quickly as possible. And no, but so I think my day-to-day routine changes each week. So I tend to focus on an area.
Yeah, all right, nice. Hey, the final's not changing, so. All right, Shai, I'll shut up.
Yeah, so I mean, I tend to change sort of week to week. So I've been working on some measurements recently, trying to set up, basically buying hardware, buying electronics, and trying to figure out which electronics will work for the measurement, getting those in, and then trying to do new measurements with those on different devices that we've designed, different electrical circuits. So that's one thing I do, and then so I'll spend some time thinking about those measurements, and then once stuff's there, I'll spend a lot of time coding. Sort of writing measurement routines, analysis of data, and then I'll spend a fair amount of time reading the literature, trying to understand quantum theory, what's going on in the world with new paradigms of quantum computing, that sort of thing. And then in normal times, there'd probably be more meetings. Like, we try to limit, and a lot of companies try to limit the number of meetings. I think Facebook as well has a day of no meetings, because it is hard even if you're working for an hour and then you go to a meeting and then you go back and have another hour and a half to work. It's really hard to do that context switching. So try to keep it so that like you have all your meetings on one day or 2 days or something like that. But yeah, so that's kind of what I do fair amount. I try to work a lot during the week and not work at all on the weekends if I can. I think that's one thing is a lot of tech jobs, there's no limit to the amount that they would want you to do. You have to limit yourself and try to keep your own bounds so you're not working, you want to have a long-term sort of sustainable lifestyle, right? So I think that's important. Yep. There's another question.
Go ahead.
Oh, I was gonna ask, when you said China was able to send like entangled data, does that mean it can move faster than light, or is that not what it means?
No. So entanglement is a special correlation of this information between two locations or two qubits. And it seems, so when you do a measurement of entangled particles, if you have two qubits and they've interacted with one another, you don't know, for example, if they're both going to be, if they're spins, if they're both pointing up, like to the North Pole, or if they're both pointing to the South Pole. You can set it up so that you know that they have to be one or the other. But there's no fundamental way to figure it out without doing that measurement. So when you measure one, you'll immediately know that the other one must be sort of pointing up as well. Or if you measure one down, then the other one is pointing down as well. And so it seems like you're doing something, even if those are separated the other sides of the universe, you're suddenly learning about particles on the other side of the universe. But to use that information, it turns out you have to communicate classically. So you still have to send information at the speed of light to use that in any algorithm. So it turns out that, yeah, you're still limited by the speed of light. There's no loophole there, no way to break Einstein's speed limit.
Cool. Other questions here from the galley.
Kind of curious about something because uh, do you think anyone's like bioengineering like transistors for quantum computing? Because I've heard that like some biologists want to create like biological computers.
Yeah, so those are different. So one thing is, I think that's interesting to understand is that uh, Moore's law is effectively dead. So Moore's law was this proposition by Gordon Moore back in, I don't know, 30 years ago, 40 years ago, that said basically every
18
every
months or
couple
something.
years,
Yeah.
yeah, it's like 18 months, something like that, the number of transistors per unit area would double. So your computer just basically got exponentially better. So double and then double and then double and double, right? So if you just wait a few years, your computer is suddenly 8 times more powerful, right, than it had been. And that, effectively is dead. So Intel and AMD are still pushing on making transistors smaller and more dense, but they're actually at the point they're hitting atomic limits where the gate length of the transistor is a few atoms. So you're really, and at that point you're hitting quantum mechanical effects that called tunneling and things that limit the performance. So they are pushing down on that still. However, what's happened is if you extend Moore's law to be a more general idea of more processing power or other metrics like the same amount of processing but for lower energy, those things have changed, and I think you have quite a number of paradigms that have come up. There's one company in the Bay Area I think is interesting called Tens Torrent. There's a guy that had worked for Intel, AMD, Tesla. He started a company that they're trying to make processors that are specific to machine learning. So it's very good at the calculations that are needed for machine learning. And one of those things means that the memory, they have massively more memory integrated directly into the processing unit. But also that there's certain operations that you do that are now inherently faster. So instead of just optimizing the code, so like usually when you're writing a program, you write the program, then you're like, oh, it's really slow because this one piece of the code is slow. So then you work to make that as fast as possible. It's gotten to the point where they now are optimizing the code along with optimizing the electrical circuit and so that's one direction, just using sort of standard semiconductor techniques. But then there is other paradigms. So one is photonics, so trying to use photons instead of electrons, basically for computation, and that has some advantages. You can have fiber optics that allow you to sort of combine processing units together, so that you're not limited to this kind of like this little die that all the transistors live on. And then the information it can be, so you can get higher speeds, higher density, things like that with photonics. And then there are more radical processing paradigms like using DNA computing. That one I don't think has gone as far, but it is, yes, there is work that's being done there. And then there are also trying to make brain-inspired circuits. So there's our brains don't actually have transistors in them. They do have spiking networks. So if your synapses to a neuron exceed a certain level, then that will send out an electrical pulse. And so there's new processors, particularly from IBM, I think, that are based on this spiking signal paradigm for computing. So instead of having like an on and off state of a transistor, it's the network sends out spikes to one another and communicate via spiking. Just effectively the derivative instead of just the DC signal. And we do live in a simulation, for sure.
Did you see Jose's question? He says, does job experience matter more than education? What do you think?
Job experience, I think they both do. It depends on what field you want to be in, right? I think I don't necessarily think staying in academics is the right thing to do if you don't want to be a professor or a teacher or do like really fundamental research. if you want to be an engineer, I think it's probably better to get a basic degree, maybe a master's, and then get into the field as quickly as possible. There's a lot of on-job training that you're just going to learn there. I think so you definitely need a college degree for most jobs now. It's just, to me, it's a question of whether it's worth getting a master's or anything beyond that. And it's, you can look at it like in an economic sense, and you can look at it in terms of, sort of happiness at your job. If you have a bachelor's degree and you're going into engineering, you're probably going to be doing the same job over and over again a lot. Sort of basic things, and that might get boring to you after a while. So you might, after that, try to train yourself and learn. You can definitely learn, on your own in the evenings or whatever once you have a job. And like within the software world, I think boot camps definitely have this intense training for a month or whatever that you can pay a company for, or there's free ones online too. They definitely help you to get hired and can help you like learn a new skill that's interesting to employers. So I think in the modern economy, no matter what job you have, you really kind of need to be learning all the time.
Yeah.
So
I got you. Well, class, maybe I'll just want to check if there's any last questions. Hopefully, did you guys actually enjoy this or not? If so, put a comment in the chat. I mean, I don't want to waste your time again bringing in speakers and having the speakers give up their time, but I have a feeling this was useful to you because I don't know. You could let me know via email. You could tell me in the chat, and let's give Loren another thumbs up. Yeah, I'll see if I can find a cheesy Zoom reaction for him there. Oh, let's go with the tears of joy, Loren. There you go. So,
well, as long as I took up some class time, you guys didn't have to do quite as much classwork, then success.
There you go. There you go. All right, everybody. So that's Loren Swenson. Hey, thanks for coming by, Loren. Hope you have enough time to eat some lunch really quick.
All right. Bye.
All right. We'll see you, buddy. Okay. All right. So let me see if I can, let me get me back on here. Hopefully, let's go to this view. What do you think, class? I don't want to waste your time doing that kind of stuff again and again, but I think that's worth it, right?
I definitely think he brought in some insight from being out of college, being in the workforce.
Yeah, I mean, that to me is the number one reason you're all here, is to eventually get a job, right? So keeping our eye on that prize is good. Sorry if it bored some of you. Obviously, not everybody's going to go to that type of career, but all right. I'll send me an email if you want, but it looks like most of you, at least a few of you, got something out of it. And all right, we could always just cut a little bit out of chapter 14 if we have to. All right, so let's go into what time is it? Let me get there we go. It's 12:51. Maybe we should just take a break right now and then come back and regroup. Sound like a plan? I guess it does to me. So, all right. So let's take a 10-minute break. I've got let's take a 60-year break. Okay. So, all right. So I'll see you guys. My clock says 12:52. So let's come back at 1:02. All right. Or 10 minutes.